Hi everyone, here's feedback on exam 2. This is for CHEM&263, and we covered all the reactions of the alpha carbon here in the chapter 21 and 22 in Klein, which includes amines as well. So the idea is you're going to usually be adding to these alpha carbons right here. Okay, usually one of them, but in some cases two of them. So let's just go through each one, and I'll give you some feedback about what I saw on the exam. So for A, I'm picturing that you would have cyclohexanone, and in acidic conditions, we have the enol form of it. And then that enol can react with the Br2, and as an enol, it is a nucleophile, and it will react with Br2 this way. So most of you got this right. This is a carbonyl with a Br at the alpha position. So, under acidic conditions, it's not as reactive as under basic conditions, so you get the monobrominated product. Whereas if we wanted polybrominated, we need to do NaOH. And so for part L here, you need NaOH rather than H+, and that's something that a lot of people missed. Okay, so for part B, once we get that and we do NaOH and heat, what would we get? And you know that this is a good leaving group, Br, so NaOH will take a beta hydrogen off. So OH minus grabs this H, and we can get a conjugated enone. So for part B, we would get this molecule. And this is particularly acidic because we make a conjugated system, so that becomes more stable. Now for part C, I want to alpha alkylate right here. I want to add this group. So probably best to do an aldol type reaction. So I want a negative charge here, but instead of attacking another carbonyl, I'll just make this into an electrophile. Maybe something like this would make this one to be attacked here. So this will come here and attack there. And so we'll do an SN2 kind of reaction. Okay, so for part C, we would want some kind of base to make the, some of you used acid, and it's okay to have enol instead of enolate, but enolate is faster. If you just did that once or twice, that's okay, but some of you used acid for all these reactions, and I'm not sure why, because almost every reaction this chapter is base, and that's because it's much faster, better nucleophile to be negatively charged. So I'm going to use NaOH. That will make an enolate ion here, and then I'll attack this backside is in an SN2 type of reaction. So I will put this benzyl halide, okay? And some of you did step 1 NaOH, step 2 this, and that's totally fine. And that's actually better so that the NaOH and this don't react together. So I would do 2 separate steps there. For part D, we want to do an aldol type of reaction. So you see that this probably was a carbonyl, and then that attacked and became an alcohol. I always use mechanism in thinking about these. So I'm going to do NaOH or LDA, either one's fine. Step 2, I want to use acetaldehyde. So now after that, you're going to have an O minus charge here, so I would neutralize it with dilute acid or water. For part E, I'm looking for a aldol condensation. So once I have the OH group here, I want to eliminate that OH, and you can do that under basic conditions. So I was looking for NaOH and heat, but you could also just put heat, assuming NaOH is still in the solution. For part F, a lot of people got this right, but some people forgot the methyl groups here, so got to pay attention to all the details. All right, so that's going to be dimethylamine, so CH3,2, and some of you use base here, but there's no need. In fact, this works better if you can activate the electrophile. So if we could protonate that, then the amine will come in and attack. Or we can use the H plus as an acid workup. So it's up to you. If you want to do this second acid workup, that's fine. But the way that we've been using it is to include the acid, but just a little bit of acid. We don't want to protonate the amine nucleophile. We just want a little bit to activate the carbonyl group. So if you do this, then you're fine. You don't need to work up steps so much. All right, now once we have this enamine, then we could do a reduction on this. So here's the amines chapter coming in. And I'm telling you, I saw a lot of people with all kinds of things here. So the correct answer is just that it gets reduced into an amine. So that's it. Some people put a methyl group here. I'm not sure why or where it came from. And some people thought the cyanide attacked at the alpha position, but there's nothing. See, in this compound, this is not a leaving group. So if you think about it, Na is this counterion. BH3 is very much like BH4, borohydride, but we're just replacing one of the hydrogens with cyanide, and so that's the only difference. So cyanide's not really a leaving group in this context. Okay, so I think also, even if you were thinking of cyanide as a nucleophile, it doesn't make sense why it would go here, because our alpha carbon, even if it was nucleophilic in some way, picture something like this happening, cyanide isn't, it would be weird for it to get attacked, I guess, So yeah, it's just not very common to see that. In fact, cyanide by itself would be negatively charged, so why would it get attacked? It would be the one to find a new electrophile, not be the electrophile. So that's the amine there for part I. Okay, for part G, this is a Michael addition. This is a conjugate addition. Here's my electrophilic center. Now, some people got this one wrong too, but just had the right idea. And so I give partial credit a lot on this page. Right here, this comes down, and then this attacks right here. This moves to here, and this goes up. Now, when you do that, you end up with the 4-carbon chain attached at the alpha position here. So that's what that turned into. And then you have your enamine that's now an imine. Now the thing is, after acid workup here in the second step, you're going to have this imine hydrolyzed to become a carbonyl. So if you forgot that part, that's -1 point. And then I saw a bunch of different things over here. Some people got it right. Some people put a methyl group here and attacked the 3rd carbon. I'm not sure why. Just lost track of the mechanism, I think. Okay, and it's easy to do unless you're consciously thinking of the mechanism or writing it out specifically without making any mistakes. It's very easy to make a careless mistake and put a methyl group right here, or get this group wrong, or put the carbonyl on the wrong carbon. So make sure you go through the mechanism, really use that. It's easy to mess it up. So for part H, it says intramolecular aldol. So what I was really looking for was that this carbon would attack here, and then you would have ring closure, and it would turn out to be a 6-membered ring. And I get that because this attacks here, 1, 2, 3, 4, 5, 6. That'll be a 6-membered ring. So I would just redraw it as a 6-membered ring. Here's another 6-membered ring for the other carbon chain. And then if you work it out, it should look like that. Okay, so this was carbon 4, 3, 2, 1. I swung this group around the other way and then attacked it here. So the ring ended up being over here. So then that's what it'll look like. So that's Robinson annulation. That's the most missed question. Still only 2 points, but I'm sure you're going to be upset that you lost 2 points on that. But if you had the right idea of it and there was one thing wrong with it, I gave you a point, but I really wanted to see the cyclization idea there. J was also missed more than it should have been, I think, because it's, actually if you know the mechanism, and I know you do, you shouldn't have missed it. So this one is where we take this, and you use NaOET, sodium ethoxide, to get that. And then you had an ester. And so I saw a lot of people just have variations, like almost everyone knew this. And then I was surprised to see only some of you did that. Okay? And so the answer was to go all the way to this. And some of you left an OET hanging there and didn't use that. Some of you did this. I don't know. Just thought everything was still there. And then some of you had something totally different. So just work through the mechanism. I know you know this stuff, but I know it's difficult on a test to not feel nervous and make mistakes. Okay, for K, it's again very important that you have the methyl groups on different sides. So for the first methyl group, you just need any kind of base, NaOH or LDA. Then you methylate CH3Br or iodide. Then the third one, you need to definitely use LDA, and the fourth one, you use CH3Br. Now on my answer key, I'm going to say LDA excess and CH3Br excess, and just do 2 steps. That's fine too. I'll make, just assuming enolate on both sides, and then I add methyl iodide to both sides. It doesn't matter bromide or iodide. Okay, if you missed excess, that's okay. I just gave it to you, but I'm just looking for this idea that you know about the kinetic and the thermodynamic enolate, that you need to make sure you do the bulky one to get the methyls on the opposite sides of each other. L, like I said, is excess NaOH and excess Br2. Again, you can do it in steps: NaOH, Br2, third step NaOH, fourth step Br2 again, just to do each side separately. Or you could just say NaOH excess, Br2 excess. And then for M, lots of different things on this one. What I was really looking for is the idea that maybe you have it's like for this one, if you had an aldehyde here on the end, and maybe that came from an alcohol that got oxidized, then you can oxidize it to the carboxylic acid. So the idea there is if I have an OH group, then I can oxidize it to the aldehyde or just oxidize it straight to the carboxylic acid. To get an OH group here, I just need to do an aldol reaction with 1 carbon. And I think a lot of people went wrong with just picking the right molecule to add here. If I want a 1 carbon aldol addition, I just need formaldehyde, C double bond O, H2. Okay, so what I was really looking for here, you could say step 1, step 2, formaldehyde. That will make that into an OH group, and then I need to oxidize it using Jones or KMNO4, whatever you want to use to oxidize sodium dichromate, something like that to make it into the carboxylic acid. Now some of you are creative and you are thinking instead of formaldehyde, you could just use something like an acid chloride. So if you had, let's say you had, this was the enolate and it attacked, so that's not there. Let's say you had an acid chloride like this, but this acid chloride is very unstable because it's only got 1 carbon, and we know acid chlorides are very unstable. So in real life, we probably would not use this compound. But just on paper, it's okay. Yeah, just in practicality, it's not really used very much. So then you would have the aldehyde, and then you could oxidize that. But I did have people, instead of even this compound, use a carboxylic acid. And that's a real no-no because this will attack here and then you'll get nothing. Okay, you'll just basically go back to there. With page 2, I'm not getting adequate explanations on these. Part of it is not saying the right reason, and part of it is not explaining specifically why that reason or how that reason answers the question. So for this one, number 2, the main thing I was looking for is when you make an enolate, you usually need a base. So let's picture we had a base like even hydroxide, or it could be LDA. And the reason why it's hard to make an enolate with carboxylic acid for basic conditions is because this hydrogen is acidic. So the best you're going to do is, instead of making an enolate, you're going to make a carboxylate, because the pKa of this hydrogen is about 5, so much more acidic than the pKa of the alpha hydrogens over here. So if there were some, if there was an R group, these guys are about pKa 20. Some of you guys even knew those values. That's great. And some of you used induction as a reason in terms of these oxygens being more electronegative and pulling charge away and making this carbon more electrophilic. So some of you thought the nucleophile or the base would even attack the carbonyl group, but that's not 100% right. The real reason is because of this reaction. So full points if you said it was the hydrogen, that would be removed because it's more acidic. Some partial credit if you said it was induction. And then quite a few of you said there were no alpha hydrogens on a carboxylic acid. And that's only true for one carboxylic acid called formic acid. But all the other carboxylic acids do have hydrogens, and when you see an R group here, and when you see carboxylic acid described as a class of molecules, it's not this specific one that doesn't have it, it's all the ones that do have it. Now, almost all of you got this right, which is which hydrogen on butanol is most acidic. So one point to point out that it's these hydrogens here in blue, which are the alpha hydrogens. But just saying that they're the alpha hydrogens doesn't explain why they're acidic. So I was looking for a very specific answer, which is that the conjugate base is resonance stabilized. Now, if you just said that these hydrogens are resonance stabilized, that's not true. The hydrogens themselves are not resonance stabilized. It's this conjugate base that's resonance stabilized. If you didn't specify that with the drawing or saying that it was the conjugate base, then I took off 1 point. But if you said resonance delocalization, I gave you 2 out of 3 points. And then if you said why this hydrogen wasn't acidic, but you didn't say why these were acidic, that doesn't explain why these aren't acidic as well. So you really need to focus in on why these are acidic. With this one as well, I think most of you knew resonance delocalization was the reason behind why cyclohexanamine was the most basic, but there were a couple issues with that. First, some people just said resonance delocalization, and then they circled this one. And so first of all, that leads to the wrong answer. Resonance delocalization stabilizes the aniline, which makes it a weak base. Another problem I saw with this is a lot of students were saying, oh, because of aromaticity, that makes this a weaker base. That's not quite true. Aromaticity is not the same thing as resonance delocalization. We don't really care that there's aromaticity in this ring. We're focusing on the basicity of the lone pair of this nitrogen, so the basicity of this nitrogen. So it's really the interaction between that lone pair into the ring, so there's delocalization over the entire molecule, not just the ring itself. Remember the example of pyridine. Pyridine is aromatic, but it is a stronger base than this molecule, which is also aromatic, and the difference being the participation of the lone pair in resonance or delocalization with the molecule. Another thing is I noticed I use the phrase a lot, in resonance. It's not really proper. I should say that the lone pair is delocalized, resonance delocalized, or stabilized by resonance. Because when you say resonance, when you say something is in resonance, it makes it sound like it's flipping, between one form and another. And it's not. The idea is the lone pair is spread out around. So really, the correct term is delocalization, not in resonance. The main issue with the first one was numbering. I think a lot of students numbered it the opposite way, to have bromo appear at carbon 2 instead of 3, but our priority group is the amine, just like with alcohols. So it should be 3-bromo, 2,2-dimethyl butanamine. For this one here, there are 3 groups attached to the N, and alphabetically, this is not a phenyl group, it's a benzyl group, so many of you knew that. This is a methyl group, and this is a cyclohexyl group. Now, some of you called this aniline. Unfortunately, this is not aniline. Aniline is this, where the nitrogen's directly attached to the ring. This one down here has a carbon and then a nitrogen. And then some of you called this toluene methylamine, but that's not right either. So this is a benzyl group, and remember, benzylic carbocations are stable because of resonance delocalization. Now what I'm going to do is list these alphabetically. So I have a benzyl, a cyclohexyl, and then a methyl. So this will be called N-benzyl because it's on a nitrogen, N-cyclohexyl And then I will call this my parent chain. So for the parent chain, you do not have to say N again. You can just add methanamine. For this group here, this is going to be my parent chain right here. And so I'm going to have a propyl group, an N-propyl group over here, and my parent chain is going to be a butanamine. Now my branches are 2,3-dimethyl, so M versus P, M comes first. So 2,3 dimethyl, and then to specify the propyl group is on the N, we have to say N-propyl. So some of you forgot the N. And then we can tack on butanamine. Now you could say butan-1-amine, but if you left it out, that's okay because it's on the first carbon. Some of you wrote N-propyl 2,3-dimethyl butanamine, so that's okay, just you're out of order though, but I didn't take any points off for that. And in fact, I was seeing so many of those that I almost marked, if you did it the right way, I marked it wrong because I was so used to seeing it the other way, and I had to go back and change that, so apologies for that. So the first step here, I was hoping you would see that the only difference is the methylation of the nitrogens. So you need CH3 and some kind of halogen like iodine or bromine is fine. Now I also for 1 point wanted you to say excess because we need 2 equivalents, or you could say 2 equivalents, either way is fine. For the next step, this is an intramolecular Hofmann. That means within this molecule there's an elimination, and the hint was beta hydrogens. So you can tell that this is the alpha position and beta position. There are no beta hydrogens. So the only beta hydrogens you can eliminate are here. And so this should take you back to E2 elimination from first quarter when you had a bulky base. And remember, you did a Hofmann elimination. Let's say you had like some kind of alkyl halide like this. And you have beta hydrogens here, and you have beta hydrogens here. If you had a bulky base, it would grab on the end, and you'd get an elimination. That was called Hofmann elimination. And your major product is your terminal alkene. So this is very similar in that because of this nitrogen group, we're going to be forced to eliminate toward the nitrogen in order to neutralize it. So your Ag2O makes the solution basic. So you have a base in solution that grabs the H, makes the double bond there, and then is able to cleave that bond. So what you'll have is a nitrogen freed up, and then you have this with the 2 methyl groups, a carbon, and then a double bond. This is your product. Now if you recognize that there was a kind of cleavage into a long chain molecule, I gave you 2 points. If you left off a group, like made this a carbonyl instead of an alkene, or forgot the methyl groups here, or maybe just forgot the entire nitrogen, I gave some partial credit because you knew the idea was intramolecular. Everyone did much better on these mechanisms. That's good. We worked through those a lot. So for basic conditions, mainly I was looking for deprotonation of the alpha carbon's hydrogen, the alpha hydrogen, and then making this enolate here. And then, so that was 2 points to deprotonate, 2 points to show this enolate, and then 2 points to show the deprotonation, protonation at the O minus to get this neutral enol. All right, so I think just 1 or 2 students thought it was the acidic, but no, it's the basic one. So I had a few students protonate this oxygen, but we would not protonate it if it was in basic condition. Okay, so here this one was to take ethoxide as a strong base and make an enolate at either there or here. Okay, but you just choose one of those positions. Then that gives you your enolate. And then that was 2 points to do that, and then another 2 points to do the nucleophilic attack and intramolecular cyclization there. And that will give you this compound. So we're almost there at the cyclization. When you do that, you'll end up with a tetrahedral intermediate, which some students went ahead and neutralized that, which could happen, but more likely this is pretty unstable, and this is a good leaving group in basic conditions. So you could just not neutralize and just do that. That will be much shorter, more efficient than neutralizing it and then deprotonating again. Okay, so 2 points, 2 points, and 2 points. For this one, it was a pretty long mechanism, so I had you start here, and some of you chose to show this step anyway, so that's nice, but I didn't ask for that, but it's great that I saw so many of you know that step, so I know you are studying it a lot. So this first part replaces the OH with the Br, which you didn't have to show. Now from there, I'm looking for the theme of forming an enol. So we had an acid catalyzed enolization or tautomerization. So you would show this, and you can assume water is in the solution. So we make this enol to start with. So that's 2 points just for the idea of acid catalyzed enolization, which is what some of you did up here, but this was basic. So this gave you a chance to show acidic enolization or tautomerization. The next part is another 2 points to show how this reacts with Br2 to alpha brominate. And I had a few mistakes here. I think I had some people do this weird thing where Br came off and these two split apart, and then this attacked here and this went up. So that's the wrong direction, so I just made a note of that if you were going the wrong direction. Some people did a weird thing where the bromide came off because it's a good leaving group, and then that left you with a positive charge here. So that's not quite right because that's very unstable. Okay, so once we have this, then to finish it off, I'm looking for the conversion of this to the carboxylic acid, so that's called hydrolysis. So I really, some people neutralize that first, but it's not necessary. Actually, it's better to keep it and attack here with water. So if you do that, you'll get hydrolysis and eventual conversion to the ketone. Now, without leaving that proton on there, some students will end up with an O- charge, but that O- is a strong base, so it would quickly get protonated, so you really shouldn't have any negative charges there. You'll have your addition of water here, and then at this point, a couple things could happen. I'd probably prefer if you deprotonated first before you did anything, and just have 2 OH groups, one of which will become a carboxylic acid. So after this step then, I would probably prefer for you just to pick one of these and just expel your Br that way. And that will give you the carboxylic acid after deprotonation. Let's say there's another water to take that H off. Okay, so that will give you that. I ran out of space here, but some of you did a really great job writing these out step by step. Some of you, unfortunately, did not show me this part, so I took off a point for that. But yeah, that was worth 2 points there. This was worth 2 points, and this was worth 2 points. So some of you showed this part, but you didn't show everything there. So there's just 1 or 2 points here and there for things like that. All right, last page. Started off with some easier ones here, just expecting you to know this is Gabriel Synthesis, so strong base, KOH or LDA, anything you want to use there is fine. And then you need a source of this 3-carbon chain here, so some kind of alkyl halide, iodide is fine, bromide is fine. And then remember, this is hydrolysis, so that we get carboxylic acids and you free this amine. So you need H3O+, water is not enough. Okay. 2 points for each of these. If you put water instead of H3O+, that was 1 point. For the next one, this is an aldol, but it's a mixed aldol. You have 2 different carbonyl groups. So hopefully you see aldehydes are more reactive as partial positive. So either this could be your enolate that attacks here, or another one of these could attack itself. Okay, so hopefully you got those as the major products in this mixed aldol. So if one attacks itself, then you'll end up with this aldehyde. And so remember, our new bond is right there. Should be 2 carbons each, so 4 carbons total. If you use the pentanone, 3-pentanone as the enolate, then that will attack and you get this guy right there. So those are the main ones. If you didn't get the major products, I took off a point for each one. And if you only put one product, then you only get half points. Okay, for the next one, Most of you were able to get the SN2 product, which is great, but you weren't sure what to do with that. So I saw some people just do that, or give me an alcohol, or some of you put an amine, but you forgot that this is a carbon that got added to the chain. So 1 point off for that. Otherwise, that was the product, and most of you got that right. Now for this one, I expected you to know this was the most acidic hydrogen, being in between the two carbonyls. So then you add one group there, and then you do it again, and you get another one added there as well. So most of you got this. And then after this, you have hydrolysis and heat, and I was hoping you knew about the decarboxylation there because we had practiced that so much in class, and for those of you in the hybrid, hopefully you guys saw that as a practice problem. So that's after step 5, decarboxylation and hydrolysis of this to and carboxylic acid, then decarboxylation to form CO2. So that came off. Now the last step is where people got a little bit stuck. That's where you have bromoform formed. So here you get all of these becoming Br. Now that's fine, but remember, part of sodium hydroxide's job is to come in and kick that out. So you actually end up with a carboxylic acid. So that was half a point if you got this, but you didn't go all the way to the carboxylic acid. So the answer is carboxylic acid. Now this one was tough. Okay, so this one I expected you to try a couple of things. One is you could try to do an imine, but notice this is secondary. You have 2 phenyl groups. So for that one, it's really hard to get a stable enamine because you have no alpha carbon here to make that into a stable enamine. So that's really not the best way to go about this this reaction. So you should abandon that and try going for an aldol reaction. So in an aldol reaction, you would want to eventually have this compound here in NaOH can attack here, and then from here you want to turn this into a carbonyl, and you want to leave this carbonyl alone. So we need to protect that. So second step will be protecting that. I had about 2 or 3 students come up with that, or maybe 2 students. So that's really great that they saw that, but not all of you guys got this far. So you had other things in mind, and I evaluated each one of those separately. Once you have this protecting group, the acetal, then you can oxidize this. So 3 would be PCC or Jones. And then you could do your imine. So you could add NHPH2 NABH3CN to make that into an amine. So it'll be an enamine, and then it'll turn into a reduced amine. After that, you want to take this group off. So you're going to do hydrolysis, so H3O+. All right, and that will take that off and convert it back to the ketone. So it was about 5 steps here. So it was about 1 point each step. But many of you got some ideas in which I gave you 2 points or 4 points, or took off 1 point here or there if it didn't make sense.